We are ready to start topic 8 in geometry. And before we get into the first section, I want to talk about how we simplify a radical. And you probably did not get to this in Algebra 1 last year, so I just want to or maybe you did, but I want to review what a radical is. First of all, when you see a symbol like that, that's a radical. That's a square root. Okay? A square root symbol is what I would also refer to as a radical. And we can take the square root of numbers like 4. Okay, what is the square root of 4? Okay, you might already know that. You might know that that's 2. Well, why is that 2? Okay, well, I can break 4 down into its factors of 2 times 2. And what square root means, it's the opposite of squaring. So since 4, okay, is the same thing as 2 to the second power, okay, 2 squared is 4, right? So a square root and squaring, they undo each other. They're opposites of each other. Like adding and subtracting are opposite operations. Taking the square root of something squared, those are opposite operations. And so you would get a value of 2. Okay, this would be 2. Or the way that you can look at it is you can say, okay, factors of 4 are 2 times 2. And since square root needs 2 of the same factor, okay, you don't ever see a 2 written here, but it's communicating that we need 2 of the same factor. I have 2 2's. And so those are able to come out from underneath the radical and give me 2 as an answer. Okay, so numbers that have nice square roots, okay, we call these numbers perfect squares, but 1 is a perfect square, 4 is a perfect square, 9 is a perfect square, 16, 25, 36, 49, and so forth. Okay, we call these perfect squares because I can take the square root of 1 and get 1. I can take the square root of 4 and get 2. I can take the square root of 9, I'm going to get 3. I can take the square root of 16, I will get 4. And so forth. If I take the square root of 25, I get 5. This would be 6, that would be 7. Okay? So these values we kind of memorize as being numbers that have nice perfect square roots. Okay? But the question becomes, what do we do when we have a number that's not in that list or not a perfect square? How do we simplify that? And that's what I want to talk to you about, is how to simplify a radical. So I might have something like the square root of 18. Well, the square root of 18 isn't in that list, so it doesn't have a nice number. But what I can do to simplify it is I can break 18 into its factors. So think about 2 numbers multiplied together that would give me 18. Some of you are thinking 2 times 9. Okay, 2 is a prime number. It doesn't break down any further. That's a prime number. It only has factors of itself and 1. But 9 is not prime yet, so we're going to keep breaking it down. 9 is 3 times 3. So we get down to what we call the prime factorization, so all numbers are prime. And now we look and say, okay, I've got a pair of 3's. That pair is going to come out from underneath the radical out front. The pair comes out as 1, and the 2, since it doesn't have a second one, has to stay underneath the radical. So I would say the square root of 18 is equal to 3 square root of 2. Now, some of you might have said, well, I don't want to use 2 and 9. I think that factors of 18, I chose 3 and 6. Okay, and you can do that also. 3 is a prime number, doesn't have any other factors other than 1 in itself. But 6 will break down into a 3 times 2. So again, we have a pair of 3's that are going to come out from underneath the radical. There's that 3. The pair comes out as 1. And then we've got 2 that has to stay under the radical. So it doesn't matter which factors you start with. We should arrive at the same answer. Okay? So maybe I do the square root of 24. Okay, the square root of 24, notice that 24 is not in this list. Okay, so I'm not going to do it on a calculator. Okay, I'm going to simplify it and have a radical in my answer. So I want to pick out things that I can multiply and get 24. Okay, maybe you said 4 times 6. 4 times 6 is 24. Neither one of these answers is a prime number yet. 4 is going to break down into 2 times 2. And 6 is going to break down into 2 times 3. Okay, and again, because this is a square root, it's like there's a 2 here. You're never going to see it written, but it's like there's a 2 there. So you need 2 of the same kind of factors. So there's a pair of 2's. So those are going to come out from underneath the radical. Okay, the pair comes out as 1. And then I've got 2 numbers that don't have pairs. So they're going to have to stay under the radical. And we're going to go back and we're going to multiply those. So that would be 2 square root of 6 is how I would leave that. Okay, I'm trying to think of some other numbers that I could use here. What about the square root of 32? Okay, the square root of 32. If I'm thinking about factors of 32, I'm going to break that down into 4 times 8. 4 is going to break down into 2 times 2. And 8 is going to break down into 2 times 4. And I just keep bringing these prime numbers down. Okay, that's going to break into 2 times 2. Okay, so I'm looking for pairs. So I've got a pair of 2's. So that's going to come out. I've got another pair of 2's. So a second 2 is going to come out. And if you bring more than one thing out, they come out, they multiply when you bring them out. So I've got 2 sets of 2's that are going to come out. And then there's this 2 that doesn't have a partner. It's got to stay underneath here. So I would multiply the 2 times the 2 and say that's 4 square roots of 2. Okay, now as you're breaking your numbers down, if you find a pair before you get to the prime numbers, you can stop there. For example, if you looked at this same problem and you said, well, I recognize that 32 is 2 times 16, and 2 is prime, and 16 is 4 times 4. I could actually stop there because I see a pair of 4's. And that pair of 4's is going to come out from underneath the radical, and the 2 is going to stay underneath. So you can do it that way as well. As soon as you see a pair, you can stop and bring that out. That's how we simplify a radical, and you're going to need to know that to work with the Pythagorean theorem.